friends, so today there are two videos that you need to watch for notes. The first one here is going to give you a lot of stuff to write down. They are the trig identities that we are going to be using throughout the rest of this chapter. I also have a PDF of this saved for you, posted, so if you want to print it, and you can honestly just use that PDF. If you don't have access to a printer, you definitely want all of these written down. So I'm going to kind of go fast. I'm going to try to explain where each are coming from. If you need to pause this at any time so that you can get things written down, please do so. So our first identities are the ones called the reciprocal identities. You've kind of been working with this already. For example, if we had sine, we knew that sine and cosecant were reciprocals. What that means is we can really write it as sine of any angle. I'm going to start to use theta, but the book will use theta or it will use x. It can use Greek letters, whatever. But sine equals 1 over cosecant. Cosine, we know as the reciprocal of secant. Tangent, we know as the reciprocal of cotangent. Now, typically, we won't use these. Let me say why. Typically, we want everything written in terms of sines or cosines or tangents in terms of our basic trig identities. So it is good to know that these exist. We don't use them as much as these next three. Cosecant is really the reciprocal of sine. If I'm doing a problem, if I ever see cosecant, one of the first things I think of is I could write that really as 1 over sine. Same with if I see a secant. I know that's the reciprocal of cosine, so I think I could write that as 1 over cosine. Similarly, if I see a cotangent, I think, well, I could write that as 1 over tangent. Know that you can use all 6 of these. Typically, we use those last 3 more often. Okay, those are reciprocal identities. You don't need to know that they're called the reciprocal identities, but I think hearing that term will help it make sense because those are the ones that they're equivalent to where they're reciprocals, where we write 1 over it. The next are the quotient identities. Quotient identities, there's only 2 of them. One is that tangent can really be written as sine over cosine. We knew this when we were evaluating on our unit circle. To find our tangent, we took our y divided by our x. You were really just taking your sine divided by your cosine. The other quotient identity is the cotangent. Cotangent is just a reciprocal of tangent, so cotangent is really your cosine over your sine. Truly, through this chapter, our goal for the most part is going to be write everything's in terms of sines and cosines. Not always, but typically if you see a tangent, you're going to write that as sine over cosine. Typically, if you see a cotangent, you're going to write that as a cosine over sine, and then hopefully we can combine things together. The next types of identities are called our Pythagorean identities. There are 3 of these. Think of your Pythagorean theorem. Think of your unit circle. If I went in the x direction, that was cosine. If I went in the y direction, that was sine, and the radius of the unit circle was 1. So hopefully it would make sense to say my x direction squared plus my y direction squared equals my hypotenuse squared, which would be our Pythagorean theorem, a squared plus b squared equals c squared. How we do that, or how we talk through this, is we say cosine squared plus sine squared equals 1. That means if you ever can get it to say cosine squared plus sine squared, you can replace all of those with just the number 1. We will use Pythagorean identities quite a bit. Pythagorean identities, just like your Pythagorean theorem, has to be squared. So if you just had cosine plus sine, you cannot say that equals 1. It must be cosine squared plus sine squared. We'll also use this one by kind of moving terms from one side to the other side. So sometimes you'll see 1 minus sine squared. Well, I could say, well, I'm using the Pythagorean theorem identities, and if I move that sine squared over, it'd be subtracting, and I could say that 1 minus sine squared equals cosine squared. So we'll use Pythagorean identities exactly as they are, but we can also move terms from one side to the other. So similarly, I could say 1 minus cosine squared would equal sine squared. Another Pythagorean identity is 1 plus tangent squared equals secant squared, and cotangent squared plus 1 equals cosecant squared. There's a way to prove those. I'm not going to spend time on that. Just know that you can, for these as well, move them around. So for instance, that second one there, if I move that tangent squared to the opposite side, I could say if I ever get secant squared minus tangent squared, I could replace all that with 1. Or that last one, if I moved maybe the 1 to the other side, if I ever had a cosecant squared minus 1, I could say that equals a cotangent squared. So Pythagorean identities, they must be squared. You can move terms from one side to the other side. Quick side note before I go any farther. Our quotient identities, our tangent equals sine over cosine, the ones that you just were looking at. Let me go back to that. Sorry here. These ones, as well as our reciprocal ones, they work if they are a single trig identity, if they are squared, if they are cubed. So for example, if this said tangent squared, I could write that as a sine squared over a cosine squared. Or if this said cotangent cubed, then this would have to be cosine cubed over sine squared. Same with our reciprocal identities. So any of these ones are okay to work with any power. Our Pythagorean ones, they have to be squared, just like our Pythagorean theorem has to be squared. Okay, the next one is our cofunction identities. These ones we will rarely use. You are only going to use it if it has something like this, and you want to replace that entire quantity. So if you have sine of pi over 2 minus theta, it has to be in that order. You can say that equals cosine. Here's what that basically is saying. Think of your sine function, your curve, your sine curve. If I were to shift it, because this is really just basically saying you're doing a shift, I could eventually get my sine function to look like my cosine function. So this is really just saying if I were to shift that sine function, it would equal cosine. Similarly, if I have cosine of pi over 2 minus theta, that would equal sine. If I had tangent of pi over 2 minus theta, that would equal cotangent. So picture your tangent graph versus your cotangent graph. Same if I have my cotangent of pi over 2 minus theta, that would equal my tangent. My secant of pi over 2 minus theta would equal my cosecant graph, and my cosecant of pi over 2 minus theta would equal my secant graph. These ones I'm not going to ask you to ever square them, so these ones are going to be straight up exactly as they are. I would only ever use these if I was given this portion of the equation and I needed to replace it. I'd replace it with something over here that was much simpler. There's our cofunction identities. Then our last identities are called our even and odd identities, or odd-even identities. They're two separate categories. Earlier in this semester, we talked about if something was an even function. Even functions were ones that were symmetric over your y-axis. And the way we proved that they were even is we said f of x equals f of negative x. What that means is this. Cosine and secant, those two, if you think of their graphs, are both symmetric over your y-axis, just like an even function is. And so they were saying f of x would equal f of negative x. How we're going to use that with our identities or with our proofs and our problems we're doing today is if you ever have a cosine of a negative, you can honestly just get rid of that negative and say it's really the same thing as a regular cosine, which is kind of strange to just drop the negative, but that's what we're going to do. Same if I have a secant. If it's a secant of a negative, I just get rid of the negative and I have a secant. These ones, if you are squaring them or cubing them or any power to them, you kind of have to be careful. For the even ones, you actually don't have to be careful. The even ones, if this said cosine squared of a negative x, it would be cosine squared of a positive x because you would basically say get rid of two negatives. Doesn't matter. Let me clarify what I really mean by that. For my odd identities, this is where we need to be careful. Odd functions said f of negative x equals negative f of x. These four functions are all symmetric about the origin. If I were to take the sine graph and I were to rotate it 180 degrees, it would match up with the sine graph. Now, here's what that means. I don't want negatives inside here. So if we ever have a negative inside here, we're going to try our best to get rid of it. And to get rid of it, we're going to put it on the outside instead. We can do that because it is an odd function. Odd functions, f of negative x equals negative f of x. So same with cosecant of a negative x, same with tangent of a negative x, and same with cotangent of a negative x. If there's a negative on the inside here, unlike these, I can just bring the negative out front. Here, if there was a negative, I could just completely get rid of it. Now here's where it has to be careful. If this was sine squared of a negative x, that means I have two negatives that I would have to put out front. So that'd be a negative times another negative, which we would know is a positive. We'll do a problem like that in our homework, but just know for your odd identities, if there are any exponents, that's how many negative signs you have to multiply by out front. Here, since there's no exponent, it's just a 1, so we would have that. One other thing I want to clarify, and I guess I should have said this when we talked about our Pythagorean identities, when you are squaring it, they're going to put the squared right after the trig function before the quantity here. If I write the squared back here, then I'm not sure, is it sine that's being squared or is it the angle that's being squared? And if it's an angle being squared, that's going to completely change where I end up on the unit circle. So if you truly want a sine times another sine, you can write that as a sine squared, but we put the squared right here. Okay, those are identities. The next video, we're actually going to use those identities. So make sure you have those so that you can reference those throughout this chapter.